Hi, this is Dr. B. In this unit, we're talking about the mole. The mole is just a number, and it's very easy to measure. We'll talk about what it is, how to use it to balance equations, molar conversions such as mole to gram, limiting reactants where you have, for example, random amounts of different reactants and you determine how much product is formed. Percent composition, for example, ammonia is 14/17. I believe that's about 82% nitrogen by mass. Both empirical and molecular formulas, some combustion analysis problems, a summary, and lots of solved problems. Let's begin. Consider a molecule of water. It would look something like this. There's the hydrogen atoms, there's the oxygen atom. What should strike you is that the hydrogen atoms are so much smaller and less massive, and in fact, the oxygen atom is 16 times more massive than the hydrogen atom. So, for example, mixing 1 gram of hydrogen with 1 gram of oxygen would not give you the same number of atoms. You'd have many more of the smaller atoms. The mole is designed to compensate for that. Here's a reaction to produce water. Notice we have 2 pairs of hydrogen. Hydrogen bonds to itself, so we have 2 H2s. We have 1 molecule of oxygen. It also bonds to itself as O2. And when they combine, not necessarily by this mechanism, but there's your 1 water molecule, and there's your 2nd water molecule. Hopefully you can see that balancing, we took our 2 pairs of hydrogen, reacted it with our 1 oxygen molecule, and what did it give us? Well, it gave us 2 water molecules. The mole is designed to show you exactly that. 2 molecules of this would react with 1 molecule of that to make 2 molecules of that. The problem is if you did it on that scale, you'd have like almost nothing. We need to scale up. It would also be nice to know how much to mix in terms of grams, for example. The mole is a scale-up factor, if you will. Not 1 molecule, but 6 times 10 to the 23rd molecule. They picked that number carefully because when you do that sort of a multiple, you'll get, generally speaking, very close to whole gram numbers for many of them. There's more to it, but that's the basic idea. A mole of hydrogen atoms has a mass of 1 gram. Now you can mass it out, and it's a decent amount. And it is 1 mole of hydrogen atoms. And remember, the mole is a number. Since oxygen is so much more massive, if you have a mole of oxygen atoms, well, you weigh it out, it's a lot more. It's 16 grams, but it's the same number of particles. And so often you have to mix 1 particle with 1. And so this would give you the correct number of molecules, atoms, whatever. And the periodic table is designed to reflect that. See that 1 gram there? It shows up as the average atomic mass. In fact, that's a better number. Same thing for oxygen. When we scale up to molar amounts, let's do that for this chemical reaction. And now we see that if we scale up to not 2 molecules, but 2 moles, well, 1 mole is 1 gram, so we're going to have a whopping 4 grams. See if you can determine the remainder of the amounts. It's going to combine with 1 mole of oxygen molecules, but that's 16 grams times 2, or 32 grams, since we are reacting it with O2. And in accordance with mass balance, no surprise, it should make 36 grams of water. And there should be a 36. There it is. So 18 grams per mole for that one, 18 grams per mole for that one, and you get 36 grams of water. In summary, a mole of helium, for example, would be that number of atoms of helium. It would weigh 4 grams. And as a little added knowledge here, it turns out that at 0 degrees Celsius, the volume of that, you could actually just measure it by volume as a gas, and it would be 22.4 liters at 0 degrees, about 24.5 liters if it's at room temperature. And that's what the mole is. It is an amount that you can weigh or sometimes even measure volumetrically if it's a gas. And this in general is the topic known as stoichiometry, which is element measuring.